So, we have discussed about the basic problem what we are going to solve in quantitative risk assessment method today. We are going to discuss about the liquid release models. We have discussed very briefly the case study in the last lecture number 5. We are talking about the group gathering station. The example is same what we discussed in an absorb study in module 1. There we discussed qualitative method of risk analysis using absorb study of the same problem. I am picking up the same example now and I am going to do QRA, that is quantitative risk assessment, for the same model where I am going to talk about liquid release models. So, it is the same process and flow diagram, just now we explained this. This has got two categories, 1, 2, 3, 4 and 5 noted in blue color are all related to pipe segments, 6, 7, 8, 9 shown in red color are all related to vessels or tanks. So, I am going to do the risk analysis for two different levels of argument, one is on the pipe sector, other is on the vessel or the tank sector. I am interested now to identify the hazards first. Quickly I will do that. The process facilities given in the problem are thoroughly reviewed. After while you review, you try to find out the most credible failure case. These cases are chosen. For example, look at the various size of leaks, compare them with the full bore rupture and look for any catastrophic rupture possible in that failure cases, such that the failure frequency of occurrence is equal to or greater than 10 power minus 9. Also look for any case which has got a lethal damage of 1% probability which is occurring outside the establishment's boundary or on the transport route, because these two issues are very important which will form what we call as a most credible failure case in a given problem. Once you do that, identify for each failure such case the release rate and the release duration. In the present example, the repression system available in the study is a manual type. On the other hand, what do you mean by this? If at all any such failure rupture occurs, the control system available to reduce that risk is actually a manual type and that takes about 30 minutes to control the rupture. That is what I mean to say here. This is an example which I have considered because this is a fact that the analysis which I am currently doing on a group gathering station has a manual type of repression system. What are the list of hazard scenarios identified by me? I have grouped them into two, one is for the pipelines and other is for the tanks. For the pipeline, I am looking for a different diameter of leak varying from 5 millimeter, 25 millimeter, 100 millimeter and a full bore rupture. In that pipeline segments, I look for an 8 inches group header pipeline coming to the heater treater. I look at the pipeline from heater treater to the ER tanks. Look at the pipeline segment from ER pumps to jumbo heater treater, look at the pipelines from jumbo heater treater to TR tanks and the pipeline from the dispatch pumps to CTF. So, I am looking for different segments of the pipeline in the process flow diagram at different units located properly, and in that pipelines I am looking for different kinds of analysis varying from a 5 mm leak to a full bore rupture. Is that understood? Now, second category of hazard scenario identified by me is basically the tank. I am looking for heater treater, the ER tanks which I call emulsion receipt tanks, the jumbo heater treater and the treated oil receipt tanks. I look for these tanks which are 6, 7, 8, 9 shown in red color in your process flow diagram, and 1, 2, 3, 4, 5 are pipeline segment shown as blue color in your process and flow diagram. In the tanks I look for either 10 mm leak and a catastrophic rupture. For the pipeline I look for 5 mm, 25 mm, 100 mm dia leaks or a full bore rupture. So, from a given process and flow diagram, I identified a specific segment of the problem. In that segment I subdivided them into two basic modules, one is a pipeline module failure, other is a tank module failure. Once I do that, I now tabulate the process parameters of these specific scenarios. For example, I look at the scenario of 8-inch group header pipeline coming to the heater treater. I analyze for a 5 mm leak size, I call that as serial number 1. The material being transported is an emulsion plus gas plus hydrogen sulfide. The volume of crude oil emulsion in meter cube per day for this specific transport is about 625 meter cube per day. The volume in cubic meter for 30 minutes, because that is the scenario of duration what I am looking at. Why 30 minutes? Because in case of any rupture, I am using a manual control system, it will take about 30 minutes for me to control that rupture. So, I am looking for what is the volume of transfer through a 5 mm leak for about 30 minutes. If I know what is the volume of transfer happening in cubic meter for 24 hours, I can find out that very easily. I already know the operating temperature of this specific liquid being transported is at 50 degrees Celsius and the pressure is about 9.8 bar, and the diameter of the pipeline in millimeters about 200 millimeters, the diameter which is transferring, and I have said 8 inches, I am converting that to millimeters, I got a fraction here anyway. I am looking for a rupture hole diameter of 5, 25, 100 and the full rupture, that is what I am looking at. So, I am looking for 4 failure scenarios 1, 2, 3, 4 for a 8 inches pipeline going to the heater treater. The length of the pipeline is about 180 meters and the pipeline is also located whether it is above ground or over ground or underground, all these pipelines are above ground. Then I look for the second scenario, which is the pipeline transferring from heater treater to the emulsion recipient tank. I look for again 5 mm, 25 mm, 100 mm and rupture, total rupture leak. I say the numbers are 5, 6, 7, 8 and so on. The emulsion is again same, the volume is 575 in this case, the volume of cubic meter per 30 minutes is again calculated and the operating temperature is slightly higher, the pressure is again slightly lower, the diameter is again 8 inches I am looking for, and I am looking for all the 4 scenarios. The length of the pipeline is about 220 meters and the pipeline is located above ground. Thirdly, the pipeline from emulsion recipient tank to the jumbo heater treater is having a volume of 176.92 cubic meter per day. The volume of cubic meter in 30 minutes is about this, because I am looking for a 30-minute scenario of leak. The operating temperature is now reduced to 35 degrees Celsius, the pressure is now slightly increased from 1.7 bar to 3.9 bar. The diameter of the pipeline is again 8 inches, the rupture I am analyzing for all the 4 cases. The length of the pipeline is about 140 meters, which I am looking now, and the pipeline is located above ground. The fourth scenario is the from jumbo heater treater to the TR tanks. The quantity is about 500 cubic meter a day, the operating temperature is about 90 degrees Celsius now, the pressure is maintained same, whereas the diameter is slightly increased, is about 300 mm now. I am looking for all the 4 scenarios. The length of the pipeline is marginally different from this with about 150 meters and the pipeline is located above ground. The last segment of my analysis for the pipeline is from the dispatch pumps to the CTF. It is actually carrying the treated crude oil now. The volume is about 960 cubic meter a day and the operating temperature is about 60 degrees Celsius and the pressure is relatively very high, it is about 20 bar, and the diameter doing that is about 200 mm, which is 8 inches diameter. I am looking for the 4 scenarios. The length of the pipeline is seriously long, because this is now a kilometer long now, and this pipeline is having another catch, this pipeline is buried in soil, it is an underground pipeline. So, from a given process flow diagram, I basically group what are the different scenarios I am looking for, what are those leak ruptures I am looking for, and what are those data which are important for me to compute the risk parameters. Similarly, if you look at the tank sector, the heater treater can have a 10 mm leak or a catastrophic rupture. I am doing these 2 analyses for all the tanks of heater treater, ER tanks, jumbo heater treater and TR tanks. You can see this scenario are common for all the 4 tanks, which are labeled as 6, 7, 8 and 9 in your process and flow diagram. Do not look at this number is actually a serial number of my risk parameters being assessed. Now the material being stored in these tanks as emulsion plus gas plus hydrogen sulfide, the volume they are handling is about 5.75 cubic meter per day, the pressure is about 1.96 bar at a temperature of 65 degrees Celsius, the diameter is about 2.3 meter, that is the diameter of the heated treated tank, the length and height of the tank is about 6.2 meter, the leak diameter what I am looking at is a 10 mm dia leak or a catastrophic rupture. I think you can appreciate from the previous lecture, if you want to really look at the liquid dispersion modeling of risk analysis, you must categorically say what kind of leak rupture you are looking at. That is how you can calculate what we call as chemical exposure index. I am looking for all the 4 tanks, heater treater, ER tanks, jumbo heater treater and TR tanks. Once I do that, subsequently I also look at the different weather conditions at which I am now considering the risk analysis. As you all understand, the quantitative risk assessment also depends on the weather condition at which you are doing the analysis and the weather condition at which the risk actually occurs in the plant. Now the weather conditions are actually estimated on the basis of the available climatic data and other meteorological data of the plant location, and they are generally available with Indian Meteorological Department, and every country has their own meteorological department which can give you the climatic data on a geographic location of the plant where you are conducting a study. In my case, the wind velocity is considered to vary from 1.5 meter per second to 6 meter per second on an average. I am also looking for different stability class. These are required in the analysis using the software. I call the B class as unstable class, it means only less sunny or more windy weather. I call the D class as a neutral class where there is a light sun availability and high wind or overcast windy night. During the night I say the class F is stable because it is a night class with moderate clouds and moderate light winds. I consider the humidity during the day as 38% and during the night as 64% for this problem. I am considering an average operating temperature as 32.8 degree during daytime and 23.7 degrees Celsius during night time. These are all different weather conditions which I will be employing in my risk analysis study subsequently. Now I do what is called consequence analysis. I am interested in doing what I am calling as event tree analysis for the liquid release. Carefully look at this flow chart, it is very interesting. It is basically an event tree analysis we carried out for a liquid release for this problem. Look at the leak or a rupture occurred at any particular point. It may be in the pipeline, it may be in the vessel. If that rupture is possible to have an immediate ignition, if that possibility is there, then you can always say it can result in what we call as a pool fire or a jet fire. So all your preventive measures should be related to controlling the jet fire which can instantaneously occur. Why? Because whenever any leak occurs from the pipeline or from the tank, if that has a possibility of immediate ignition, then it may result in pool fire. Now if there is no probability of immediate ignition for that particular chemical or the liquid being released, then check whether is it confined within a specific area. This confinement, if it is possible, then is it possible to have a delayed ignition? Can you do a delayed ignition? If the delayed ignition is possible, then it may result in what we call as vapor cloud explosion. If the delayed ignition is not possible, then it can have what we call as a safe dispersion. If on the other hand your liquid being ruptured is actually not confined and it has an immediate ignition, then it may again set in what we call as a jet fire or a flash fire. If that immediate ignition is not possible, then we can say the liquid is ready for safe dispersion. So it is a very simple event tree analysis which is also one of the method of risk analysis. Incidentally, it can tell you from a simple flow chart of this kind, it can tell you what kind of exit will be there as a consequence of your accident. It can cause either a pool fire, it can cause a jet fire, it can cause a vapor cloud explosion, or it can be safe for dispersion, it can cause a flash fire, or it can say for dispersion. When these situations are occurring or when they are possible, that can be easily seen from a simple analysis what we call as event tree analysis. Once I do that, I input this data in the software, because these are all very cumbersome data to do a risk analysis. I use a specific software, I input this data. Let us look at the results and argue and discuss on the results further. For example, let us say I am looking for one specific result, which is a jet fire. Jet fire is measured in terms of heat radiation, which is given as kilowatt per square meter area, and I look for all the scenarios of 8-inch pipeline, 8 inches group header pipeline to heater treater, pipeline from heater treater to ER tank, pipeline from ER pumps to jumbo heater treater, pipeline from jumbo heater treater to ER tanks, and pipeline from dispatch to CTF. In all these regions of 1, 2, 3, 4 and 5 shown as a blue color in your process and flow diagram, I am analyzing for all the 4 scenarios of 5 mm leak, 25 mm leak, 100 mm leak and rupture. Now I am looking for downward damage distances in meters for different stability class, that is F in the night, B in the day and D in the day, and I also look for different radiation levels of 4, 12.5 and 37.5. These are all different levels of radiation which can be sustained, which cannot be sustained in kilowatt per square meter. For example, the radiation level is about 4 kilowatt per square meter, can go for a longer distance and can be sustainable. If the radiation level is about 37.5 kilowatt per square meter, it is intolerable, therefore that is having more risk level. And if that happens in night at 1.5 F, if it happens in day at 1.5 B, that is a stability class. It can happen in night in the day at 6 D, again a stability class. If we look at this and do the analysis in the software, I get a result of this tabulated value here. In the tabulated value, I look at these red levels of 100 mm leak. This is identified as a very undesirable level of consequence, which I get from the jet fire. You may wonder how I arrived as a specific red band. I will come to that at the end of this presentation. Similarly, I look at for the tanks, heater treater, ER tanks, jumbo heater treater and TR tanks. I look for the scenarios of 10 mm leak or a catastrophic rupture in all of them. So basically this is considered as number 6 in your process and flow diagram. So number 6, number 7, number 8 and number 9, which is shown in blue color in your PFD, and in that I am looking for both the kinds of possibilities of 10 mm leak and a catastrophic rupture, and I again look for downwind damage distances for different stability class as it did for the pipeline segment, and I look for the values obtained from the software, and I am seeing there are no red band available in the software. You can also compare these values with respect to the pipeline leak scenario. They were all basically the values related to from 14 to 33 or 35, whereas in the earlier case the values have gone as high as 300, which has become a red band. Now I look at the second scenario, which can be a pool fire. You may wonder how a pool fire can be caused. We have already given you the equations in the third module, lecture 1 and 2, when a liquid can become a pool fire, when a liquid can cause a jet fire, when a liquid can simply become a safe dispersion, etc., by giving 2 examples. Kindly look at them back again. Ascertain the conditions for your liquid to become a pool fire. If it becomes a pool fire, again for the pipeline segment and for the tank segment, I have done the analysis using the software. I have got the results. Again I do not have a red band values here. Unfortunately, when I look for the catastrophic rupture on an ER tank for a pool fire, I get a very high value. This depends upon the frequency and consequence which are input in the risk analysis software, and I get the numbers as high as 850. So that becomes a red band here. Similarly, I look for the third scenario, which I called as an explosion. This is generally measured in terms of overpressure as bar. I look for the value of downward damage distances, and there are some standard threshold value beyond which it is considered as very high. So, if we look at the pipeline segment, again the 100 mm leak size has a higher undesirable value varying from about, let us say, 450 to as high as 820. So, it gets a red band, the remaining values do not get a red band on the pipeline segment. Subsequently, we also did this for the tank segment, and unfortunately I do not have any red band in the tank segment at all. After doing these kinds of analysis for jet fire, pool fire, etc., now I start doing what we call as frequency analysis. I am looking for the frequency failure calculations. How do I get that? For example, I look at the pipeline segment. Let us say I consider a pipeline, group header pipeline going to the heater treater. I am looking for all the 4 scenarios, 5 mm, 25 mm, 100 mm and the catastrophic or whole point rupture. We already know the pipeline is of length of 180 meters. The failure frequency per meter per annum, which has been taken as a statistical data based on experience of a similar plant, is given here. So, what does it mean? If you consider the ester data, you get an average failure frequency of 1.7 10 power minus 5 per meter per annum. Now, what is the total basic failure? I can simply multiply the frequency per meter per annum into the length of the pipe. I will get the total basic failure in frequency per annum. So, the parameter of length of the pipe is now eliminated from this column to this column. So, this is nothing but the product of this multiplied by the length in meters. I will get this value. Now, the blocking system is being given a number which is varying from 0 to 1, and I have selected this number as 0.99. If this pipe segment has any non-return valve and any other emergency situation to attack or to counteract the problem, I have given the specific weightage of these two as 0.06 and 0.99. If the segment has any fire protection system, I give a credit to that, and ultimately I calculate the frequency per annum as 9 into 10 power minus 5. So, that is the frequency. For example, the frequency per meter is about 1.7 10 power minus 5. I multiply this for the whole length, I get very high as 3.06 10 power minus 3. Considering the safety factors present in the system, I ultimately compute the failure frequency as 9 10 power minus 5. Remember that this is a computed failure frequency, this is the frequency failure only taken from a previous experience of any such plant. So, this failure frequency given due weightage to the existing system safeguards available, I get what I call calculated failure frequency from the software directly. Now, I get this frequency for different pipeline segments in the PFD for different scenarios identified by me, like 5 mm leak, 25 mm leak, 100 mm leak and rupture. You can always see here, if you look for a whole pipe rupture, the calculated frequency is relatively different from that of what you take for the 5 mm leak, and that is true for all the pipeline segment. Similarly, I have also done for the tank segment, that is heater treater, ER tanks, jumbo heater treater and TR tanks for both the scenarios of 10 mm leak and catastrophic rupture. The total basic failure frequency based upon previous experience of similar plant is available here. The blocking system is being given some weightage, the efficiency of controlling system has been given some weightage. Based on these, I compute the calculated failure frequency per annum as 1.36 10 power minus 3 for a 10 mm size leak of a heater treater, and I can do that for almost all the vessels of the tanks for different scenarios and so on so forth. Once I do that, now I estimate what I call as an individual risk and a societal risk. How do I get that? The risk of fatality of a person at a specific location, assuming that the person is continuously exposed to the risk at that location. That is the basic assumption for individual risk. It is expressed in terms of risk contours. Ladies and gentlemen, I told you most of the softwares will give you the output of risk analysis in a graphical format as well. So, what we call as risk contours. It is given by a simple expression here. IRPA is summation of LSIR for the whole plant multiplied by FL, whereas IRPA is what I call as individual risk per annum, which I am interested to calculate. LSIR is a location specific individual risk. So, the plant can have risk at different locations, therefore, I sum up this for the whole scenario of the plant, and each location specific individual risk as a fraction of time of an individual spends in that location. For example, your plant has different location A, B, C, D, E. An employee may spend in a working hours of 8 hours, he may spend 4 hours in location A and about 30 minutes in location E. So, each location specific has a fraction of time what he spends on that location. I multiply that with the location specific individual risk available at that location, and I do this for the whole plant. I get what is called individual risk per annum. I can also compute the societal risk. Actually, it is a measure of the risk that the events pose to the local population, taking into account the distribution of population in the local area. This is generally given in terms of Fn curves, where Fn is basically expanded as the curve between the likelihood of the events outcome that affect a given number in a single incident. Now, I have a population data for the specific GGS where it is situated. I am masking the specific location without identifying the name of the plant. So, I have a data which I have taken from a geographical data of a specific plant. This is the plant which I am looking for. This is another segment of the plant where the nearby village, which is in the closest vicinity of this plant. I am looking for a GGS, group gathering station, located in this area. I am looking for the effect or the consequence of this leak, if at all it occurs, on the neighborhood village as well as this. The plant data is been available here in different building, the security block, the administrative building, the plant area and the nearby village. This figure is very interestingly remembered by you. We now call, after computing risk, whether the risk is acceptable to us. We call this an acceptable criteria. IS 15656, which is actually a code of practice for hazard identification risk analysis, the annexure E in this code summarizes the risk criteria adopted in some countries. You can look either this as a reference book for computing or let us say calculating the risk acceptance levels for your problem. Alternatively, you can also look at the Netherlands risk acceptance criteria. To achieve the above risk acceptance criteria, Allard principle was followed in this specific case study. We have already seen the specific triangle. There are red region, yellow region and green region. Now, what is interesting here is, if your risk calculated in the previous slide from the software falls in this band of 1 10 power minus 6, we say that it is an Allard region. If the risk falls in the value of 1.0 10 power minus 8 or lower than that, then we can say it is a broadly acceptable region. If the risk is much higher than 1.0 10 power minus 6, for example, let us say 1 10 power minus 5 and so on, then the risk is on the unacceptable region. So, you have calculated risk for every event on the pipeline segment, every event on the tank segment for different scenarios. Now, pick up only those numbers and see where these numbers fit in the Allard triangle. I have done that. For example, if you look at the pipeline segment of A, B, C, D and so on for different scenarios, I see that these values of 10 power minus 7, minus 6 are in a different region, whereas 10 power minus 5 and minus 4 fall in the red region, which is an unacceptable region. So, what I did is, after I get the results, I summarize them for individual risk and societal risk. Then I check whether these numbers exceed the value given in Allard triangle. Those values exceeded given in Allard triangle has been highlighted in red here, and the corresponding scenario have been carefully looked at. For example, the pipeline segment which is carrying the fluid from heater treater to ER tank, if it ruptures at 25 mm leak, then the risk exposure level to the individual will be unacceptable, to the society also will be unacceptable. That is how you will interpret the results what I am showing you in the present slide. I look at that for other scenarios, I look at that for different vessels. You can see some of the risk values are falling on the red region in the LR triangle, which is unacceptable risk by a specific standard. In this current example, I am following the Indian standard, and incidentally if you look at the rupture on the vessel or the tank segments for all the 4 scenarios, maybe 10 mm leak and catastrophic rupture, all these risk levels computed are very much falling on either on the alarm region or on the safe region. So, ladies and gentlemen, starting from a process and flow diagram, you can easily estimate actually the risk as a number, which will tell you whether that risk, if at all a rupture occurs, is acceptable to an individual or to society in per annum basis. As I said, ultimately the risk should be given as a risk contour in a graphical format. This is the solution what I am getting here in the graphical format. The individual risk what I get here is about 1.36 10 power minus 4 per annum, which is shown in the blue color here, and this is an acceptable region, this is an alarm region, and that is a safe region. So, you get basically a contour, and this is actually the epicenter of the problem where the plant or the GGS is located. This is a scenario for the pipeline rupture from heater treater to ER tank, which is already in the red region. If I look at the societal risk, I used to express this as an F1 curve. F is the number of fatalities plotted in the x axis, and N is the frequency plotted in y axis in average per year, and this is number N, that is why we call this F1 curve. And you look at the scenario, the societal risk what I get is 1.44 10 power minus 4 per annum. The green line what you see here is a combination of both, is the maximum risk criteria and the minimum risk criteria is given in blue color. So, what I am getting here is a combination of these two, and my problem is falling somewhere here. Therefore, there is no societal risk except for one rupture which is on the pipeline segment as discussed. So, the maximum tolerable risk per year is about 1.0 10 power minus 6, and the negligible risk per year is about 1.0 10 power minus 8. This is what I got from the present study. In the installation, the following scenarios fall under the category of unacceptable region: leak of 25 mm pipeline from heater treater to ER tank, leak of 100 mm leak diameter of the pipeline of 8 inches dia in the same segment, rupture of the pipeline, then leak of the pipeline from jumbo heater treater to TR tanks, rupture of the pipeline in the same segment, then leak of the pipeline from dispatch pumps to CTF, and rupture of the pipeline from dispatch pumps to CTF. These are all the scenarios which have been given a specific number of 6, 7, 8, 15, 16 depending upon the serial number of what you have analyzed in the previous record. Once I get this, I will talk about what is called risk mitigation. The unacceptable risk level is basically due to the amount of flammable material available. So, our job is to avoid any major catastrophe, so that the material available should be brought down. This can be easily achieved by implementing various remedial measures, one of which is being tried in the specific example is outflow duration. As you remember, the control mechanism what I have is operable for about 30 minutes because it is a manual system. So, what I am recommending for this specific case is either use a semi automatic blocking system which can control the outflow duration to 10 minutes, or use a complete automatic blocking system which can control the outflow duration to about 2 minutes. What does it mean? In case of any rupture, if I am using a manual system to control that mechanism, the outflow duration will be about 30 minutes. So, there is an extensive delay in controlling that particular mitigation. If I use a semi automatic, I can control the disaster in 10 minutes. If it is an automatic, I can use the control mechanism in less than 2 minutes. Remember that whatever control mechanism you have in a system, you have got to give a weightage in analysis for what we call as the blocking system. If you remember, I have given this weightage as 0.99. For example, if I use an automatic system, then I could have given as 0.1 or I could have given as 0.05. As the number is higher, it indicates me that the system is more manual and less automatic, and the flow duration is very high. Once I do that, then I get for different system, the manual system has a risk level for individual and societal as this. If I implement semi automatic, I get individual and societal risk as this. If I implement completely automatic system, I get individual and societal risk as this. You can very easily see for all those identified scenarios, you will see by implementing semi automatic or automatic from the manual system, the risk level for individual as well as societal is greatly reduced. From 10 power minus 5, it has gone to 10 power minus 9. So, this is how we simply do a quantitative risk assessment for a simple case study of a group gathering station, which is demonstrated for you. There are the following recommendations we can make for this problem: to make the existing blocking system of the plant into either a semi automatic system, then in that case follow the regulations as the pipelines connecting heater treater, jumbo heater treater and pipeline to dispatch CTF are to be equipped with hydrocarbon leak detector and transmitter. That is what we call as semi automatic blocking system, because these detectors will pass on the information to the control room, and then the control valves can be triggered off to operate and control. So, it takes 10 minutes for example to do this operation, make it effective. We can also recommend installation of pressure transmitters at both ends of the pipeline. We can also recommend the pipeline should be provided with a control valve at the inlet, which can be remotely operated from the control room of the whole plant. The control room should be manned round the clock. The emulsion recipient tank and the TR tank can have system in place such that the spilled over contents in the dike are transferred to other tanks instantaneously. The starting and stopping of pumps should be carried out under constant supervision. There should be a periodic inspection and thickness measurement on the pipeline deposits and vessels to know what kind of process scenario is happening. Once I do that, I have a summary sheet here. If I say for exposure duration of 10 seconds and 30 seconds, for radiation level of 1 lethality of 21.2 and 9.3, for radiation level of second degree burns, then it is about 16 and 7, for radiation level of first degree burns it is about 12.5 and 4. The heat radiation varying from 1.6 to 37.5 will have a different damage level on the people. For 1.6 generally no discomfort is being given to the public. For about 12.5 onwards there is a 100% fatality even for a short time exposure. So, the equipment what you can use to control them, the minimum energy required for melting of plastic is what you have got to do. Use the minimum energy required to ignite wood, sufficient quantity to use major accident to the equipment. The peak core pressure varying from 0.3 to 0.01 in the problem will cause the damage type from heavy damage to a minor damage. The minor damage can cause a crack in glass, can be seen like that. The heavy damage can be seen as a major disaster to the plant equipment structure. So, this is the final summary what you will get as a recommendation and in the graphical format for a QRA. So, ladies and gentlemen, we have completed a QRA study for a specific example, and I have given you some list of references for your future reading, and all these are very interesting, available in the literature as open source as well as on the chargeable basis. Kindly go through them in detail, try to identify and practice a QRA for your segment, and that will be the success of listening to this lecture. If you have any questions, you are happy to post it at NPTEL IIT Madras. Thanks.